I hope you all get a chance to watch my Monday recording, and Qingyang has answered all your questions for our Monday lecture. So during our Monday lecture, we went over a discussion in what exactly is the heat of formation, or delta F H naught. That's a standard heat of formation. Right, so we gave you this list of procedures that you need to take, that these are mental procedures or actual procedures you need to take in order to measure the standard heat of formation. So in our last lecture, we went over this list that includes like what exactly are there in each of every state and what process or what measurement we're taking in each of the transformation steps. We went carefully over this part in how to calculate the change of your enthalpy at different temperature and pressure. We also went over the setup for calorimetry in that's how people use calorimetry to measure the delta H of the reaction. Now, there are one more thing that we sort of left over, which is the transfer between real gas and ideal gas. So remember, the standard state for ideal gases are standard states for gases are ideal, right? But at 1 bar, ideal gases doesn't exist at 1 bar. It only exists when your pressure goes to 0, right? So we need to somehow take consideration of that transformation between ideal gas and real gas. So we'll talk about that first, and then we'll go over some calculation and see how do we take care of like multiple step reactions using the Hess law. So I moved the rank of things a little bit in our annotated note. So let's get started talking about the first topic here. So what we're trying to address is how do you take consideration of the enthalpy of a real gas versus the enthalpy of an ideal gas. So again, we'll do our derivation here and just try to work it through, like what exactly is happening at different states. So the initial state here, right? So let's assume we start from our real gas at our standard pressure, which is 1 bar, and at some random temperature T. Right, so at the initial state, we have H real at temperature T and standard pressure P naught. Now, the first step is to reduce the pressure while keeping the temperature same. Or the other way to put it is we're saying the first step here is an isothermal reduction of pressure. From P naught, which is 1 bar, to 0 bar. So we're keeping the temperature same and reducing the pressure back to 0 bar. And then the result of that transformation is now you have a real gas at the same temperature T, but now the pressure is reduced to 0 bar. Step B here, where imagine you have some kind of magic wand that eliminates all the intermolecular forces in your real gas, right? So the difference between your real gas and ideal gas is ideal gas assumes your gas molecules or gas atoms do not interact with each other, while real gases, you have intermolecular forces. So we'll eliminate all intermolecular interactions. And then what we have after our step B are ideal gases at 0 bar and the same temperature T. Well, obviously, the last step we want to take is an isothermal increase of pressure from 0 bar back to P naught. And what we end up getting is ideal gas at P naught. So the difference between the H real and the H ideal at T and P naught is something we're looking for. or what if we put it in equation, what we're looking for here is delta H ideal minus real equals to H ideal at T P naught minus H real P naught. Right, so final minus initial. Or if we're starting from a real gas and you end up with ideal, if you start from ideal gas and you end up with real gas, then it's just a negative of that number, right? So what we have, so in this case, we have 3 different steps. So effectively, what we're looking for is delta HA, which is this isothermal reduction of P, plus delta HB, plus delta HC. And we'll go by it one by one. So the first thing first, that's the isothermal reduction of pressure from P naught to 0 bar for a real gas. All right. So in this case, the reaction we're using here is we're talking about an isothermal reduction of pressure. We're talking about the change of enthalpy with respect to pressure at constant T. So using one of our Maxwell relationship, give us this partial derivative of H over P at constant T equals to negative TV alpha plus V. All right, so alpha is something you can measure experimentally. Temperature, volume are also something you can measure experimentally. Or if we write it out, we have delta HA equals to H real at T 0 bar minus H real of T P naught. And you use this integral, use that relationship there, and we're getting, by taking the integral of P, we start from P naught, we end up at P, get negative TV alpha plus V dP. All right, so that's our first step here. The key equation we're using here, the reason we know why to use this equation is to think about what is the nature of this process. Right? So the nature of this process is an isothermal pressure change. So we're talking about the relative change between your enthalpy with respect to pressure at constant temperature. And then go back to the Maxwell relations and also the partial derivatives we derived to find out the correct equation to use. So whenever you're encountering these problems, think about the nature of that transformation and find the appropriate equation to use. All right, so that's the first step, delta HA. Now we have our real gas at 0 bar at that certain temperature. Our next step here, we're looking at eliminating all the intermolecular forces. So this one is a little bit more qualitative end. So if you think about the process where P is approaching 0, so that means the pressure is approaching 0 for your gas. So when the pressure is approaching 0, that means your gas atom or molecules are just infinitely apart from each other. So their distance are like really, really far away from each other. Right, so when pressure is approaching 0 from the qualitative end, we have the intermolecular forces approaching 0 because the gas molecules are becoming far away from each other. So what we have is when our pressure approaches 0, our intermolecular forces are approaching 0 between your molecules. Or what does that mean is when your pressure is approaching 0, your ideal gas and real gas are effectively the same to each other, right? So that boundary between ideal and real gases become like diminished when your pressure approaches 0. Or the other way to put it is your delta HB equals to your H real at T 0 bar minus H ideal at T and 0 bar. And this term becomes 0. Wait, okay, it should be ideal minus real. All right? So this one we know, this one is 0. And what about the last one? Now we have the ideal gas at 0 bar, and we're trying to increase the pressure isothermally of that ideal gas from 0 bar back to its standard pressure. So now we're talking about ideal gases. We spend lots of time talking about ideal gases, and now imagine what is one of the property of ideal gases. So when we're talking about ideal gases and its enthalpy, one of the things we know is that the enthalpy of an ideal gas and also the internal energy of an ideal gas only depends on temperature. All right, so what that means is, well, H of ideal gases only depends on temperature. So for an isothermal processes, we have delta T equals to 0. So obviously your delta HC will also equals to 0 for an isothermal process. All right. Or if you want to write this out, what we have is delta HC is from like T1, T2, Cp is a function of T dt, right? So your temperature is not changing, so your enthalpy is not changing. So taking together, what do we have? Now we have the difference between your ideal gas and real gas. Only the first term counts. Only the first term, which is the change of your enthalpy for the isothermal reduction of pressure from your standard pressure 1 bar to 0 bar for your real gas. Only that term is non-zero. Or taking together, we can end up with a final expression for what we want, delta H, which in this case is real to ideal. So your final state is ideal minus real. That equals to H ideal minus H real. And that gives you from P naught to 0, negative TV alpha plus V dP constant T at constant T. All right, and in your textbook, it also expanded this expression by writing out alpha. So alpha equals to 1 over V. Partial derivative of V over T at constant P and N, or isobaric compressibility. And you have that expression of P naught to 0 minus T, partial derivative of V over T at constant P N plus V dP. All right. So in this process, what we're doing is just telling you how people actually measure the standard heat of formation for a specific substance. So that is a combination of using thermodynamic laws and also using meticulously set up for your calorimetry experiment. All right, so it's a combination of thermodynamic laws and experimental measurement. We then have those thermodynamic table for the heat of standard heat of formation for different substances. All right, so this is a quick summary on what we talked about before. I know this slide is a little bit messy, but just like know what exactly we're doing at every step. We are talking about the difference. Initial state is like all your reactant in its in its standard state. So your gases are hypothetically ideal, its pressure is standard. And our final state are just like real gases and also the standard pressure, right? So we're talking about the heat of formation for these substances and how people get to those thermodynamic tables. Any questions before we move on to using the thermodynamic tables? Nope. Okay. So with that in hand, we then move on to the more application end of using the thermodynamic table to solve for something that's, that will be useful from a chemistry point of view. So the law we're trying to introduce here is called Hess's law. It reads the overall enthalpy change of a reaction is equal to the sum of the enthalpy change for the individual steps of the reaction. All right, so we're talking about for a multiple step reactions, the overall change equals to the sum of each step taking place. So let's look at an example together, which is, well, Haber process. Right, so Haber process is being used to produce ammonia. So starting from hydrogen gas and nitrogen gas, we have two different steps to form the ammonia. So in each of these steps, we can calculate the change of enthalpy, the reaction enthalpy, by survey the thermodynamic table. So for example, in this case, the first reaction, so delta H naught of your step 1 equals to your product minus reactant, or in this case, it's much easier to call this one an intermediate. So the delta H naught of your intermediate N2H4 gas minus your reactant and in the process, just keep in mind to use your stoichiometric coefficient minus 2 times delta H naught of H2 minus delta H naught of N2. So you can check the table. You have that table in your textbook appendix. I forgot the page number, but it's at the end of your textbook. So use that table, and we can find out this reaction to have a delta H for 95.4 kilojoule per mole. And when we have a positive delta H, what it means is our reactant has a lower enthalpy compared to your product, so this reaction is an endothermic reaction. I mean, at least the first step is an endothermic reaction. And we can do the same for the second step. We'll just do it together. So we have delta H naught, step 2. That is your product. So 2 times delta H naught of NH3 minus your intermediate and reactant. You can plug in the data and get the number to be negative 187.6 kilojoule per mole. Now your delta H now is a negative number, so that tells you we have an exothermic reaction. So using the Hess law, when we're talking about the overall reaction for the Haber process, we're adding these two reactions together. What we end up having is the overall reaction where you're reacting 3C of H2 gas with 1C of your N2 gas gives you 2C of NH3 gas. So C, that's the extent of reaction, if you remember, right? So one more of reaction taking place. So our delta H overall that's the 2 delta H naught NH3 minus the 3 delta H naught H2 minus delta H naught N2. And this delta H naught overall will also equals to our the first step and second step. All right, and the way to think about this process is now this intermediate will cancel out when you add your delta H for step 1 and delta H for step 2 together, and this will cancel out with each other. So it doesn't show up in your final expression. And if we're talking about the numeric value, then we're just adding these two numbers together to be 95.4 minus 187.6 kilojoule per mole. So that's the overall reaction. And this reaction overall is an exothermic reaction. All right. My annotated note is more detailed, but I think this one is good enough, unless somebody has any questions. Okay. And if we look at the energy profile for what is happening here, just to have a more qualitative understanding, right, we start from reactants. The first step is endothermic. So our first delta H1 is endothermic, it's positive. Right, so my reactant is like 2, H2, and N2. And at the intermediate state, that is our N2H4, and we reacted with another molecule of H2. We have our delta H2 going from intermediate to product, and that is exothermic. Right, and the overall reaction is just the addition of your delta H1 plus delta H2 for this reaction. So the idea of the Hess law is very straightforward. I guess the more difficult part lies here is try to know, is to know how to write a balance equation and know how to cancel out your intermediate along the way. So let's look at an example together. So this one is using the Hess law, trying to solve for a multiple step reaction. So it's asked you to calculate the standard enthalpy of hydrogenation of liquid benzene. All right. So for this reaction, we need to first write out the reaction of interest. So what do we have? We're talking about the hydrogenation of liquid benzene, or what we have is C6H6, so that's the molecular formula of benzene in liquid form, plus hydrogenation, we're reacting it with hydrogen, so 3H2 in gas phase, and it leads to the product, which is your cyclohexene. Right, so these are my reactants. And your cyclohexene is our product. And we might not give you, for example, the heat of formation of each of the reactant here. And for example, one of the power of Hess law is now instead of only using the heat of formation, you can also using other forms of the standard enthalpy to derive the overall reaction, right? So for example, in this case, we're giving you the standard enthalpy of combustion of your liquid benzene, liquid cyclohexene, and the standard enthalpy of formation of water. Now, what does these terms mean? So when you see the problem is giving you like standard enthalpy of combustion of liquid benzene, just write out the combustion equation. So in this case, we're talking about delta H1, we're talking about a reaction of C6H6, liquid benzene, burning in oxygen to give you carbon dioxide and water. And we balance that equation. So that's 6, 3, that's 15/2. So we're talking about the enthalpy of combustion of 1 mole of liquid benzene here. And that's what our delta H1 is. Likewise, you can write that the reaction, the combustion reaction for liquid cyclohexene. And what we have is C6H12 liquid plus oxygen plus CO2 goes to CO2 and water. So that's 6, 6, 9. So this one is a quick refreshment that you will need to balance chemical equations. So if you forgot how to do it, just practice a little bit. It will come back to you. And at the end, we have the standard enthalpy of formation of water. So when we're talking about the standard enthalpy of formation of water, what we're saying is starting from its reference point, right? So H2 plus 1/2 of O2 goes to liquid water. All right. And now we're looking at the overall reaction. What do we have here? We want to have our benzene in our reactant site. So this one is one of the reaction we want to write down. So that's our first reaction. We want to have our benzene on the reactant site. And then we want to have our cyclohexane on the product end. So we're talking about the reverse of this reaction. So I'm just going to move it to the other end. Right, so since the first one is just delta H naught 1, second one, we're talking about the reverse reaction. So that is the negative of delta H2 that's reversed. And in this process, we are having water involved in the process, and we need to balance our equations. So what do we have here? We have 3 water that's forming on the top, and on the bottom, we have 6 water. So we need 3 more water on the right-hand side to balance the overall reaction. Right? So the overall reaction, we do not have water in your reactant or product. That's an intermediate. We have to balance your water in that case. So we observe it and we find, okay, so we have 3 more water on the right-hand side. So that is the 3 times, well, H2 plus 1/2 O2 goes to water. So that's 3 times delta H formation of water, so, or this delta H3. All right, and if we look at the overall processes here, what do we have? On the left-hand side, we have C6H6, and my water cancel out, so 3, so this one is effectively 3, 3, 3. These 3 and the 6 water cancel out. And in this case, the 6 carbon dioxide cancel out. And your oxygen, which is 9, this one is 15/2, 3/2, your oxygen also cancel out. So the overall reaction we have is the C6H6 liquid plus 3H2 goes to the C6H12 liquid. And since we write out this set of equations, right, we have the delta H of the reaction, of the hydrogenation reaction, equals to delta H naught 1 minus delta H naught 2 plus 3 times delta H naught 3. All right, and that's what our coefficients are here. And you can do that calculation to get a final number for the heat of the hydrogenation reaction. I think I missed a node here. That's just for standard state. All right. So the Hess law part is pretty straightforward. As long as you know how to write balanced chemical equations and you're careful canceling out all your intermediate along the way, I don't expect it to be challenging to anyone in this class. Or if we want to even more generalize your delta H of the reaction coming from the delta H of every specific step using the Hess law, you can always write delta H of the reaction equals to summation of n delta Hn. So that's for the n-step reaction. All right, any questions? Nope? Okay. I always feel that chapter 5 is a nice little break between calculus and the make a link between thermodynamics and the real chemistry. And before we jump into my next lecture note, I want to quickly mention the temperature dependence of reaction heat. So when we're talking about delta H, the enthalpy of the reaction, it has a dependence on temperature, right? So delta H is a function of temperature. And what exactly is that dependence? So we can use the heat of capacity to quickly estimate what is the temperature dependence of your reaction heat. So the way to do it is remember what we have, the delta H of the reaction equals the summation of all the coefficients times the molar enthalpy, standard molar enthalpy of each of your reactant or product involved in the reaction. Or the other way to put it is what we have is delta H naught as some function of T. If we take the derivative of dt, so we derive by dt on both ends of the equation, we have delta H naught over dt equals to the summation here. Your coefficient is independent from temperature, so we don't care about it in the derivative. And you have our dH naught dt. Wait, this one should be delta H naught. Or since we're talking about the standard state of a specific substrate or your or reactant or product, so that standard state will be ideal. So what we have is you have the heat capacity equals to the partial derivative of H over T at constant P. So your Cp, standard state, equals to dH over dt. Or the other way for this one to say is delta H naught over dt equals to delta Cp naught. All right, so we're talking about a relationship between your enthalpy and your heat capacity, and it's connected by the change of temperature. Or it's more straightforward to just remember it. It's like delta H naught. You can do it by taking the integral between T1 and T2 of your delta Cp naught as a function of T over dt. And in this case, when we're talking about heat capacity and measuring the heat capacity's dependency on temperature, that's something experimentally can be measured. So typically that's expressed by polynomial. So your Cp molar heat capacity, standard molar heat capacity equals to like A plus Bt plus Ct squared plus dt third, etc., etc. So I mean, it's not that complicated. It's just like something people can do by plotting your heat capacity versus temperature and do a polynomial fit to get that relationship and those coefficients. So this one is just a quick mentioning just to make you aware that, okay, so the heat capacity is dependent on temperature, and as a result, your enthalpy is also dependent on temperature. And typically, we're using our appendix data or tabulated thermodynamic data to solve this kind of problem. So if we have an example question here, so that says use the appendix data and neglect the temperature dependence of your Cp naught to estimate your delta H naught at 1000 degree for your reaction going from like oxygen gas to 2 atomic oxygen gas phase. So here are the appendix data that you can also get by reading your textbook. I'll also give you those data in case you need it. Or chances are for our next midterm, we will have a thermodynamic table at the beginning of the exam, so you can always refer back to that table. So I just want to make sure we're using the same table, that's all. All right. And by looking at it here, these are the information you can get by just reading that table. It also tells you we can neglect the temperature dependence. So what do we have? So first of all, we can calculate the delta H of the reaction of this oxygen O2 decomposed into atomic oxygen at 298 Kelvin. Right, so that is just using the coefficient of the reaction and also the standard enthalpy of the reactant and product to do that calculation. So what we have is 2 times the product, 249.170 minus, well, that's 0 in kilojoule per mole. So that's the enthalpy of the reaction is 298 Kelvin. And then you can calculate the change of your heat capacity, or delta Cp naught. Yes?
Why are the units kilojoules per mole if you're technically like multiplying by like 2 moles?
This one is just like, we're just minors. So, okay, so first of all, coefficient doesn't have any unit. Yes. Next one, we're talking about the change of your heat capacity, right? So delta Cp naught equals to, again, product minus reactant. So 2 times 21.912 minus 29.355. We have joule per mole per Kelvin. And at the end, we're trying to take consideration of your temperature change by using delta H naught 1000 K to be equals to your delta H naught 298 K plus your delta T times the Cp naught in this case. We're assuming it's temperature dependent, so whatever you calculate is Cp times the change of temperature. You can do that calculation and check it with the number there. So this part should feel like a little bit of just plugging numbers, but know what number to plug in and know how to use the tabulated data. But at the same time, just keep yourself connected, like how those tabulated data are being generated, right? So we went over that careful derivation in how do you measure the heat of formation of a specific substrate. And that's being used to create those thermodynamic tables. So know how to use the thermodynamic tables and also know what people are doing to create those thermodynamic tables. All right, any questions? Nope? Okay. This part, I mean, again, every time I see no question, I assume you fully understand it or you're completely lost. So for this topic, I think it's fully understand it. Okay, next one. Let's get started a little bit on lecture 14. I don't think I can finish any of it, but just get started. So lecture 14, we're talking about 5.7 and 5.8. So we're moving on from enthalpy to talking about entropy, right? So we went over use of your thermodynamic table to find out the reaction enthalpy or reaction heat. And what about reaction entropies? So before we do that, we want to first introduce the concept of conventional entropy. So entropy is different from enthalpy, which is like enthalpy is directly related to the molecular nature of your substrate. But entropy is something that's it's not defined for a specific state. So when we're talking about for the conventional entropy, we're taking a difference between that standard state, like 1 bar and the 298K. We're comparing that entropy of that substance at that specific state to a reference point. So we're talking about the change of entropy between a reference point and at some point you're interested in your tabulated data. Or the way to think about it is when we say conventional entropy, or these are the entropy you will read from the thermodynamic table, what we're effectively saying are these are relative entropies. All right, so going back to the definition of entropy, you have, well, ds equals to dq reversible over t. So taking the integration on both ends, what we will have is, well, s, or delta s, equals to the integral of 1 over t dq reversible. And at standard state, P naught equals to 1 bar. Right, so the pressure is constant at that standard state. What we can write is delta S superscription naught equals to integration of dq reversible over t. Now, in this case, when we're having the standard state, the pressure is the same. So your dqp equals to delta H equals to Cp dt. So we've done this derivation several times, and you should now be familiar with how we get it from the original definition to this integral of Cp over T dt. All right, so that's a quick review. Just refresh your memory on entropy. Then what do we have? Now we're arbitrarily set the molar entropy for each element in a stable condensed form in state pressure equals to 1 bar when temperature is approaching 0 Kelvin equal to 0. So what that means is we're saying Sm of 0K and standard pressure. So when this temperature, well, let me just write temperature here. So when this temperature approaches 0K, this term equals to 0. And that is only for elements in stable condensed form. So a stable condensed form, for example, carbon, we're referring its stable condensed form to be carbon in its graphite form. So some of the things we will be talking about, again, just refresh your memory here. That little knot means we're talking about standard pressure equals to 1 bar. This small subscription M tells you that it's the molar entropy. And T here, that's the temperature in Kelvin. Just refresh your memory a little bit. And then we'll use our third law of thermodynamics to give this random condensed form a little bit more information. So, we have 5 minutes. Let me just quickly introduce you to the third law of thermodynamics, and we'll do that again at the beginning of our next lecture, which is next Monday. So, in the third law of thermodynamics, it starts from an experimental observation. So in an experimental observation, what we have is when you plot the slope of, when you plot delta G naught or delta G of a reaction versus temperature. So the slope for that curve of a reaction goes to 0, when your temperature goes to 0, okay? All right, so that slope is telling you the change, your delta G naught over your temperature at constant pressure when your T is approaching 0, this derivative goes to 0. This one should be partial derivative, sorry. And in our Gibbs relation, one of the things we find out is delta S equals to, or negative delta S equals to the partial derivative of G over T at constant P. So taking together, what do we have here is that from that experimental observation, we can say that delta S equals to your, state 2 minus state 1. That is the partial derivative of G2 over T at constant P plus partial derivative of G1 over T at constant P. Or that is our delta partial derivative of G over T at constant P. And this term goes to 0. That's an experimental observation we made. Or the way to put it is we have, when T approaches 0, the delta S of any reaction goes to 0. Or the other way to state that third law of thermodynamics is the Nernst-Simons statement. So that's where they first claim that third law of thermodynamics, that for any isothermal processes that involves only substance in internal equilibrium, the entropy change goes to 0 when T goes to 0. So it's like when you have a reaction, like two perfect crystals, both approaching 0 Kelvin, and the reaction of those two pure crystals, when temperature approaches 0 Kelvin, will have your entropy change goes to 0. All right, so this is just a quick introduction to the third law of thermodynamics. We'll do that again at the beginning of our next lecture, which is on Monday. Do we have any questions before we move on? Nope. Okay, well, we don't have any classes this Friday, so have fun on Veterans Day, and I'll see you next Monday.